Good evening, everyone. I'm Dr. Shalini Hanok, Associate Professor, Department of Electronics and Communication Engineering, ATME College of Engineering, Mysore. Today, I'll be discussing another experiment of Digital Communication Lab BECL 504, that is, generate a 16 QAM modulation and obtain the QAM constellation. Before going to the experiment, we'll see the theoretical aspect of it, that is, what is QAM. QAM, a form of modulation which is widely used for modulating data signals onto a carrier used for radio communication. QAM is a signal in which two carriers shifted in phase by 90 degrees are modulated. The resultant output consists of both amplitude and phase variation. So, whereas in other techniques of modulation like QPSK, BPSK, and all those things, we will be concentrating on one parameter, either it is phase or amplitude. But when it comes to QAM, we will be concentrating both on amplitude and phase variations. Hence, it may also be considered as a mixture of amplitude and phase modulation. QAM, why QAM? The main aim is to save the bandwidth. How we are going to save the bandwidth? Double sideband even with the suppressed carrier occupies twice the bandwidth of the modulating signal. This is very wasteful of the available frequency spectrum. QAM places two independent double sideband suppressed carrier signal in the same spectrum as one ordinary double sideband suppressed carrier signal. Types of QAM. So it exists in both analog and digital formats. The analog version of QAM are typically used to allow multiple analog signals to be carried on the signal carriers. It combines phase modulation and amplitude modulation in the form of modulation known as quadrature amplitude modulation, in short called as QAM. Digital formats of QAM are often referred to as quantized QAM. It combines phase shift keying and amplitude keying in the form of modulation known as quadrature amplitude modulation QAM. So this is the block diagram wherein we have I channel, Q channel input and an oscillator, 90-degree phase shift. Then after that, in demodulation part, it's a reverse process. So the phasor diagram is as shown, wherein both amplitude and phase will be changing. There are different types of QAMs. The different forms of QAMs are 16 QAM, 32 QAM, 64 QAM, 128 and 256. So this is the constellation diagram for all different QAMs we have 8 QAMs where 8 points are there, and this is the variations of 8 symbols, that is from 0 0 0. As we have seen in QPSK, it has 4 symbols 0 0 0 1 1 0 and 1 1. In 8 QAM it will be the 8 symbols, so the combination will vary from 0 0 0 to 1 1 1 binary data. In 16 QAM it is 4 bits, it is 4-bit variations of 16 combinations, and we also have 32-bit, 32 QAM, 64 QAM, and we also have 128 to 56. Anyway, we will not look into it. Since the syllabus is about 16 QAM, we are going to only concentrate on 16 QAM. And here this is the 4-bit datas, which are different combination of 4-bit datas represented on different constellations, and 2-bit for one I channel and 2-bit for Q channel. Then it is going to be combined. This is the block diagram of the QAM. We have random generator, general QAM modulator. So similar to QPSK what we had done. This is how the block diagram looks like. Now we are going to see the constellation diagram of it, how to generate it. So initially we have to go for MATLAB, then go for Simulink, then you have to take blank and we have to drag and drop. Since I have already done the block diagram, I'll just open the block diagram which has already been done. So this is just a drag and drop. We have to drag and drop random integer generator and rectangular 16 QAM and rectangular 16 demodulator QAM AWN channel, and we are going to see only the constellation diagram here. So once everything is organized and everything is connected, so we are going to set some parameter. When in random integer generator, you have to go and set the size as 16 since it is a 16 bit QAM, and the sample frame we will be giving it as 1000. Then in rectangular QAM, we will go and we will set here it is MRA number as 16, and the normalized method we will be taking average power. Then in AWN channel, so if for 16-bit QAM, we are going to take from 10 to 14 dB, so we will take 12 dB here. And in the demodulator part, again we have to set it to MRA as 16 and normalize method has average and apply. So in constellation, we have to go to the constellation. Sorry. Now we are going to run the. Okay. So now we will be simulating it. For simulation, we have to go to the run and we have to run. And now we can observe the constellation diagram where we have different quadrature, different points and different quadratures. Here if we see there are 16 points on the quadrature. Here 16 points. So this is at the before the this is before the AWN channel, and this is this diagram is before the AWN channel, constellation diagram 1, and this is outside at the demodulated point. So now we can also measure the constellation diagram after introducing AWN noise also. Now, if you are going to observe the constellation diagram after introducing AWGN, that is additive white Gaussian noise, we can observe the noise being present in all the 16 nodes. So, that's the experiment viewing the constellation diagram of 16 QAM. Thank you.